But mutations can sometimes be good things. As we see with endogenous retroviruses, I mean, they're totally a mistake that we do not want functional.
Well, are
but
they
yet
a
we can
mutation?
still use that and to use those. Well, you don't just get a retrovirus that suddenly gets turned into a placenta. I mean, you have mutations that accumulate over time that eventually the end product just happens to be what we call a placenta today. But absolutely, mutations can be good things. They aren't always deleterious.
Doesn't that make the assumption that all placental mammals are only placental, generating because of an endogenous retrovirus?
Absolutely. But that entire endogenous retrovirus isn't functional. They just slowly domesticated a protein from an endogenous retrovirus over the course of time.
Well, that is what the theory says, that once the viral DNA entered the genome, then it was domesticated. Now that sounds authoritative, but it's a mechanism that's assumed in the word domesticated. This is the theory. This is the assumption that's made. And like I said, I have no problem with making assumptions. But to say that we know that an endogenous retrovirus is the reason there's a third branch of mammals.
You know, if you knock it out, you don't get babies anymore. They do it in sheep.
You don't get babies anymore. So there's no other pseudogenes that are there that could do this?
Well, it is sufficient. It is necessary and sufficient.
Today.
Yeah. But mutations can be good.
Is an endogenous retrovirus a mutation?
Yeah.
Where does it come from? Outside, it comes from a virus. It's not something generated within the genome itself. Now, once it's in there, it can. Right?
Yeah.
Oh, okay. So endogenous retroviruses aren't a mutation.
They're a change in the original genome.
They are genetic material that's borrowed from another organism, true?
That isn't normally there.
That isn't normally there. Okay, so it's coming from another deck of cards. Okay. This is some kind of a marker that shows that, yes, we're related to chimps. It does make an assumption. And I'm not saying assumptions are bad. In science, you must make assumptions when you don't know something. The assumption is made that the only way to really get these things into the genome and into the germ cell lines is by common descent. And that two separate species that never were separate shouldn't be showing the same endogenous retrovirus DNA sticking there in their chromosomes. Well, how many of these are actually orthologous? How many of these ERVs actually are the same ones and are on the same location? And what are the chances of that being able to happen if there's 98,000 of these that exist in us, and however many in chimps, maybe 200,000 of them exist in us? Let's take a look at something from an article from last year, from the Proceedings of the National Academy of Sciences. It says that these things could go back 85 million years, according to DNA clock testing that evolutionists use. Lentiviruses could be very ancient indeed, 85 million years. Now, viruses are known to mutate at an incredibly rapid rate, maybe 1,000 times, maybe 1,000,000 times faster than other creatures' DNA, like yours. Now, if these viruses have been multiplying and mutating at these incredibly accelerated rates for what this article claims is 85 million years, well, 1,000,000 times that is 8,500 trillion years. And that's in people years. That's different from dog years and people years. I'm talking about people years and virus years, okay? They've had the equivalent of 8,500 trillion years. And what are these lentiviruses? What are these endogenous retroviruses today? They are still viruses. They haven't written any new code with new traits or new genetic information. They haven't advanced any. They've done exactly what the creationist paradigm said. By shuffling genes and by innovation of genes by accident, they can make horizontal changes, but they can never get past that limit to change that I was talking about.